So hi everyone, I'm Jiaqi Gao from Alibaba. Today I'm going to talk about Alibaba's HPN 7.0, a data center network for large language model training jobs. Over the past years, we have seen a great advance in the large language model field. It is estimated that the transformer size has grown 750 times every 2 years. In contrast, hardwares are struggling to keep up. Moore's law only provides 2 times performance boost in the same time period. Therefore, in the age of LLM, for tech companies, exascale computing power is the core competitiveness, which stems from accelerator scale up and scale out. However, achieving such exascale computing power is not as simple as building a large-scale accelerator cluster. If we naively increasing the scale of the cluster without carefully designing it, the achievable performance might drop, and the linear scaling efficiency decreases as the scale goes up. This is because LLM training workload brings new challenges that we haven't dealt with in the traditional data center cluster. Here is a snapshot of next traffic in the LLM training job for 2 consecutive minutes. We can see that there are several new characters we haven't seen before. Firstly, the traffic has low entropy, which means one NIC only sends to a small portion of hosts in the cluster, rather than the high connection count in the traditional workload. Secondly, the traffic volume is high. We can see that in the active phase, the traffic takes entire 400 gigabit per second bandwidth. This creates high pressure for every component connecting the source and the destination, including the NIC, optical modules, links, and switches. Thirdly, the end hosts are globally synchronized, which means the entire cluster experiences such on and off patterns. Lastly, one training job is large-scale and long-lasting, which means such stress test will last for weeks or even months. If we directly apply this workload to a general-purpose compute cluster, it will cause 2 major issues. Due to the traffic's low entropy character, a general-purpose compute cluster causes a lot of hash imbalances, which will cause low link utilizations and longer flow completion time, which slows down the entire training job. And also because the training job is globally synchronized and stress tested, the entire cluster is prone to failures, which means the training job will be frequently restarted and the entire cluster's availability is low. After studying the challenges and understanding why previous solutions does not apply, we now present how Alibaba builds their large-scale accelerator cluster to achieve the exascale computing power. And we believe there are 2 key solutions. The first one is to provide a consistent high-performance interconnect. To achieve this, we build HPN 7.0, which stands for the 7th generation high-performance network. It is a predictable data center network for AI infrastructure. We specially designed the data center architecture to overcome the drawbacks in the general-purpose compute cluster. Firstly, HPN 7.0 is a 2-tier topology. Here, we have a collection of accelerator servers in the cluster. We only connect them using 2 layers of switches. Compared with the traditional 3-tier topology, HPN 7.0 is able to provide lower latency and lower hash complexity, which achieves higher performance and simpler path selection for the transport layer protocol, and also reduce the maintenance, monitoring, and debugging complexity. It is also a multi-rail topology, which means that each accelerator connects to one dedicated switch in the first tier. For example, the orange accelerators in each server all connect to the orange switch. The blue accelerators all connect to the blue switches. In the first tier, different rails are not connected to each other. This design leverages the scale-up network within each server and maximizes the fan-out of the first-tier network. This design also maximizes the scale of the one-hop network that completely removes the congestion and hash collision. Especially, we name the first-tier network a segment. In a segment, all the accelerators on different servers with the same index are directly connected to the scale-out network. All the accelerators in the same servers are directly connected in the scale-up network. Therefore, there is no hash collision nor congestion between the accelerators within the segment. There are multiple segments in the HPN 7.0 topology, and the second-tier switches provide inter-segment connectivity. The second-tier switches can either connect the segments in a full mesh fashion, which maximizes the bandwidth resource between the segments, or connect in a rail-only fashion, which maximizes the scale of the topology. HPN 7.0 is also a dual-plane topology, which means that each accelerator in the server are connected to two separate networks that are completely isolated from each other. For example, in this figure, we can see that each accelerator connects to the orange and blue network at the same time, but they are not interconnected. This further increases the scale of the topology and also provides redundancy, since one plane can be the backup of the other. At last, HPN 7.0 is a front-backend separate topology, which means the CPU and the accelerators are also isolated in the network. This avoids the interference between the CPU traffic and the accelerator traffic, which further increases the performance of the communication between the accelerators. As for the scale, HPN 7.0 is able to connect up to 130K accelerators. We use 51.2 terabits per second single ASIC switch for maximized simplicity and robustness. Since each accelerator requires 2 times 200 gigabit per second bandwidth, HPN 7.0 can support up to 1,000 accelerators per segment and up to 128 segments. For full mesh second-tier topology, HPN 7.0 is able to support 16 segments. For rail-only second-tier topology, HPN 7.0 supports up to 128 segments, which translate to more than 130K accelerators. In the end host, we also introduced a non-stacked dual-ToR solution. From the operating system's perspective, there's only one bound device connecting to both planes at the same time. There's only one IP for the two planes, and the switches and NICs communicate with each other to ensure the fast switching and the failures. The traditional stacked dual-ToR solution creates a strong dependency on synchronization and requires a direct link between the two switches, which violates our dual-plane design philosophy. We developed a non-stacked dual-ToR solution. We deeply cooperated with our switch vendors to implement a customized LACP module to realize this feature. Connecting all the designs together, we achieved no single link failure disconnects the accelerator from the network. Here shows the performance curve when the link failure and the link flapping happens during our production network. We can see that compared with a single ToR solution, our dual ToR solution greatly reduces the impact of network anomalies to the overall training job. So this is how we build a consistent high-performance interconnect. The second key to achieve the exascale computing power is computation and communication co-optimize. The co-optimization starts from the hardware. In HPN 7.0, we in-housely designed and developed hardwares for customization, fast iteration, and stability. We designed our own 51.2 terabits per second switch, improve its cooling solution for better stability. We also developed our own 200 and 400 gigabit per second modules. We also designed and developed our own programmable NIC to implement our high-performance transport layer protocol. We also optimized our software stack and transport layer protocol for optimal performance. We developed Alibaba's own collective communication library called Echo, which is a globally coordinated and topology-aware collective communication library that's specially optimized for HPN 7.0 topology. It is able to provide better performance and stability than the previous solutions. We designed and developed Solar, which is a high-performance multipath transport layer protocol that is able to leverage the abundant path and saturate all the links in the topology. As for the switch, we customized AliNOS, which provides a white box hash function and path selection functionality to the transport layer protocols to minimize the potential hash collisions in the network. We also developed the Nimbus container network, which provides an IPv6-based low-overhead virtualization and multi-tenancy functionalities for our customers. For the management stack, we built platform for AI, Pi, that is able to perform topology-aware job allocation, scheduling, and communication and computation overlapping to maximize the overall efficiency for the entire training cluster. Also, we provide a host and network co-design management system for fast failure detection, localization, and mitigation. In Echo, we deployed accelerator servers hang and slowness detection and localization monitors, which can detect servers that are slowing down the entire cluster in real time. In the transport layer protocol, we provide a fast rerouting mechanism under transient network congestion and short-term link failure scenarios to maintain its high performance. In the switch, we provide high-precision network monitoring and failure detection mechanisms to provide instant feedback from the network to the end host. In the container network, we designed a host monitoring and end-to-end connectivity probing monitor to query the network from the server's perspective. As for the management platform, Pi provides a centralized fault detection, localization, isolation, and fast job recovery mechanism, so that when failure happens, the faulty machine is quickly removed from the cluster and the job is resumed. Summarizing all the aspects up, HPN 7.0 provides generation leap in performance and stability. From the CCL's perspective, HPN 7.0 is able to increase its performance by up to 100%. As for training jobs in different scales, HPN 7.0 is able to increase the training throughput by 14.4%. HPN 7.0 has been deployed in production in Alibaba Cloud and already shown its superior performance and stability. According to our online measurement, HPN 7.0 provides 96% linear scaling efficiency, 98.22% cluster availability, which means the active time cluster is used for training jobs rather than experiencing failure detection and recoveries or performance fluctuations. It is able to continuously operate for more than 3 weeks without drop interaction, and is able to recover from failures in minutes. This journey never ends. Thanks to all the hard work from Alibaba's engineers and developers, we are able to provide superior linear scaling efficiency up to 10,000 accelerator cluster. But if we continuously increasing the scale of our cluster, the existing solutions might need further optimizations to continue such a trend. In order to achieve this, we call for talented people and a close partnership. Thank you for your listening.